Welcome to Relax Story, a peaceful place where gentle stories help you leave behind the worries of the day and drift into a calm, restful sleep. Each soothing narration is designed to relax your mind, ease tension, and bring a sense of comfort and peace. If you enjoy listening, please like and subscribe, and feel free to share your thoughts or story suggestions in the comments. Now, close your eyes, take a slow, deep breath, and let Relax Story guide you into a night of deep and peaceful sleep. (11:38 a.m. January 28, 1986. The sky above Cape Canaveral was clear. At Launchpad 39B at the Kennedy Space Center, everything appeared ready for what was supposed to be another landmark day in the history of America's space shuttle program. The weather that morning was unusual. The temperature hovered around 35°. It was the coldest launch day the shuttle program had ever attempted up to that point. Overnight, ice had formed on multiple structures around the launch complex. Technicians spent hours inspecting the pad for ice accumulation before giving approval to continue launch preparations. Yet the images appearing on national television were not images of frost and ice. They were images of anticipation. Millions of Americans were watching live. Hundreds of thousands of students sat in front of television screens in classrooms across the country. Many schools had organized special viewing events. Few NASA launches had ever attracted this level of public attention. America's focus that day was not really on the scientific experiments or technical objectives planned for orbit. It was focused on one person. That person was Krista McAuliffe, a history teacher from Concord High School in New Hampshire. She had been selected from more than 11,000 applicants in the Teacher in Space project. For the first time in history, an ordinary citizen who was not a test pilot, not a professional scientist, and not a member of the military would travel into space aboard a space shuttle. Once in orbit, she was scheduled to deliver 2 live lessons to students across the United States. The idea carried enormous appeal. Space was no longer a place reserved exclusively for experts. It had become something a high school teacher could reach. Krista McAuliffe's students were watching. The astronauts' families was watching. Teachers across the country were watching. NASA officials were watching. The national media was watching. A teacher was about to become a symbol of American education. No one knew that millions of children were about to witness the exact opposite. The countdown approached 0. Challenger left the ground at 11:38 a.m. Eastern Time. All 3 main engines performed exactly as designed. The 2 solid rocket boosters generated immense thrust, lifting the entire vehicle away from the launch pad. Everything appeared normal. Then came the number that would haunt the history of American spaceflight. 73 seconds, not 73 minutes, not 73 hours, just 73 seconds. It is less time than it takes to brew a cup of coffee, less time than a short news segment, less time than many of the routine tasks that fill an ordinary day. But it was enough time to end 7 lives. The audience did not know the cause. They saw only a rocket climbing into the sky. Then, at the 73rd second, something unusual appeared. A flash of flame emerged from the right solid rocket booster. Within moments, the structure of the vehicle began to fail. The tanks containing liquid hydrogen and liquid oxygen were destroyed. Challenger broke apart at an altitude of roughly 14 kilometers, while traveling at nearly 2,000 kilometers per hour. Everything happened little more than a minute after liftoff. High above Florida, a massive white plume expanded into the shape of a giant Y. The image was broadcast live across the nation. June Scobie, the wife of Commander Dick Scobie, saw it. Krista McAuliffe's family saw it. The families of the other crew members saw it. Students in New Hampshire saw it. Millions of Americans saw it. Below, spectators were still waving and cheering. Above them, the cloud of smoke continued to spread. Very few people understood what had just happened. About 6 minutes after the explosion, at the White House in Washington, D.C., President Ronald Reagan was preparing for the State of the Union address, scheduled to air later that evening. His prepared remarks already included a reference to Krista McAuliffe as a symbol of the American spirit. At approximately 11:44 a.m., Communications Director Pat Buchanan entered the Oval Office and informed him that the space shuttle had exploded. Reagan asked only one question. Was that the one with the teacher on board? No one needed to answer. The entire country already knew. But that explosion is not where this story begins. It is where it ends. The 73 seconds were only the final chapter visible to the public. What truly killed Challenger began long before the spacecraft ever left the launch pad. Not on the morning of January 28, 1986, but months earlier, perhaps even years earlier. By 1986, America was far removed from the moment Neil Armstrong stepped onto the moon. 17 years had passed since Apollo 11. The generation that once stayed awake through the night to watch humanity's first footsteps on another world had grown accustomed to seeing spacecraft on television. What had once felt like a miracle was slowly becoming familiar. NASA faced a different challenge as well. The agency had reached the summit of public prestige through the success of Apollo. But historic victories often come with a difficult problem. Once the greatest goal has been achieved, the next question is always, what comes next? NASA's answer was the Space Shuttle program. When it was approved in the early 1970s, the shuttle was presented as the future of American spaceflight. These would no longer be rare expeditions prepared over many years. The new ambition was to make access to space routine, repeatable, and as regular as commercial aviation. The promises were compelling. The shuttle could be reused. Launch costs would fall dramatically. The system could support scientific research, deploy commercial satellites, carry out defense missions, and even serve educational programs. Space was being described as a new highway opening before modern society. In some of the most ambitious projections, NASA envisioned dozens of flights every year. Even in 1985, internal forecasts still pointed toward a target of roughly 24 missions annually by the end of the decade. On paper, it was a revolution. In reality, it was far more complicated. Every shuttle launch was a massive engineering campaign. After returning to Earth, each orbiter required lengthy inspection and maintenance. Components had to be replaced. Minor deviations had to be corrected. Technical issues appeared again and again in places nobody expected. The system was marketed as a routine transportation vehicle, yet it remained far more experimental than the public was led to believe. The gap between promise and reality continued to widen. That gap created something more dangerous than any individual technical flaw: pressure. In 1985, NASA completed 9 shuttle missions, the highest annual total the program had achieved up to that point. Yet compared with the goals that had been publicly promoted, the number still fell well short of expectations. Every launch delay pushed the entire chain of missions behind it further into the future. Commercial satellites had to wait. Contracted customers had to adjust their plans. Defense-related missions continued to pile up. Delays were no longer viewed as purely technical problems. They were becoming organizational problems. Congress wanted to know what return it was receiving from the enormous investment poured into the shuttle program. The White House monitored progress against promised objectives. NASA found itself constantly having to prove that the system justified the budget it received. That was when a quiet contradiction began to emerge. NASA was no longer just a scientific research agency. NASA was defending a promise. A program promoted as the future of humanity was becoming increasingly governed by schedules, planning meetings, and performance metrics that had to be met. Then the White House introduced a unique opportunity, or perhaps a unique source of pressure. In August 1984, President Ronald Reagan announced the Teacher in Space project. The official goal was simple. A teacher would travel into space to inspire American students, encourage science education, and spark interest in technology among a new generation. Beneath that goal was another reality. By the mid-1980s, spaceflight no longer carried the same cultural magnetism it had during Apollo. The public had grown accustomed to shuttle launches. Liftoffs were no longer events that brought the entire nation to a halt. NASA needed a new face, not a military astronaut, not a famous scientist, an ordinary person. More than 11,000 teachers from across America submitted applications. After multiple rounds of selection, the field was narrowed to 10 finalists. The winner was Krista McAuliffe, a high school history teacher from New Hampshire. Barbara Morgan was chosen as her backup. Krista's selection quickly generated exactly the response NASA had hoped for. She appeared on national television programs. Newspapers followed her every step. Schools tracked her training and preparations. The public began paying attention to the Space Shuttle program again. A history teacher, a multi-billion-dollar space program. Both were now tied to the same launch. The moment Krista joined the crew manifest, Challenger ceased to be just another technical mission. It became a symbol. On the evening of January 28, 1986, President Reagan was scheduled to deliver the State of the Union address to the nation. NASA had prepared extensive media coverage centered around Krista McAuliffe in space. The concept was obvious. An American teacher orbiting Earth on the same day the president addressed the country would create a powerful image. No one issued an order to launch at any cost. No document instructed anyone to ignore safety procedures. Yet everyone understood the significance of the moment. A scientific mission was now carrying the weight of a political event. Technical decisions were beginning to exist in the same space as public image, media expectations, and performance pressure. Even so, the greatest pressure had not yet arrived. It came from the schedule. STS-51L had already been delayed multiple times before its final launch date. Sometimes because of weather, sometimes because of issues at the launch site. sometimes because of problems involving the crew compartment, sometimes because maintenance requirements emerged at the last minute. Every scrubbed launch consumed money, manpower, and time. Every delay made the schedule behind it even more complicated. The media began mocking the recurring postponements. Some news programs openly questioned whether NASA truly operated as efficiently as it claimed. The most dangerous thing was not the criticism. The most dangerous thing was what it did to the organization's mindset. When a system is constantly required to prove its competence, cancellation gradually begins to look like failure, even when it is the safest choice available. During the night of January 27 and the early hours of January 28, 1986, Florida experienced an unusually severe cold snap. Temperatures dropped to levels rarely seen in the region. Ice formed throughout the launch complex. Water systems had to be kept flowing continuously to reduce freezing in critical pipes. Photographs taken the following morning showed ice hanging from the launch tower and coating multiple metal structures around the pad. A question began to emerge. Should the launch be delayed once again? It should have been a technical question. By that point, however, it had become an organizational question, a public image question, a question shaped by years of accumulated pressure. Ice covered the launch site. But the thing that had truly frozen was the ability to say no. More than 2,000 miles away in Utah, an engineer named Roger Boisjoly was staring at data he had been tracking for years. He was not afraid of another launch delay. What frightened him was the possibility that the launch would proceed. In November 1985, at the Johnson Space Center in Houston, a photographer captured the official crew portrait of STS-51L. It was the kind of image the Space Shuttle program produced during its most optimistic years. The photograph was prepared for media campaigns, for articles about the future, for interviews leading up to launch day. In the front row sat Michael Smith, Dick Scobie, and Ronald McNair. Behind them stood Ellison Onizuka, Krista McAuliffe, Gregory Jarvis, and Judith Resnick. All of them wore dark blue flight suits. All of them were smiling. No one in that photograph knew they had less than 3 months left to live. What makes the image remarkable is not the arrangement of the crew or the mission patches sewn onto their uniforms. What matters is the purpose it was originally meant to serve. This was a photograph about the future. It was created to introduce the people who were about to travel into space, representing America's knowledge, technology, and confidence. After January 28, 1986, that meaning disappeared. The photograph was no longer about the future. It became a memorial. Looking back years later, people no longer see a crew. They see 7 different stories, 7 different lives, 7 separate paths leading to the same morning. At the center of the photograph sits Francis Richard Scobie, the mission commander. He was born into a working-class family in Washington state. His father worked as a mechanic. Machines were part of Scobie's life from an early age. After joining the United States Air Force, he became a test pilot, a profession that demands the ability to make decisions under conditions most people will never face. Over the course of his military career, he flew more than 45 different aircraft. One of them was the X-24B, an experimental vehicle that operated at the edge between the atmosphere and space. It was a place where even the smallest mistake could carry serious consequences. Scobie spent almost his entire life learning how to manage risk in the air. He understood speed. He understood pressure. He understood the limits of machines. Yet the greatest risk aboard Challenger did not come from the sky. It emerged from a meeting he was never invited to attend. Seated to Scobie's right was Michael Smith. If Scobie represented experience, Smith represented patience. He had served as a Navy pilot during the Vietnam era and accumulated thousands of flight hours across multiple aircraft. In 1980, he was selected by NASA. For many people, that would have been the destination of a career. For Smith, it was only the beginning of a long wait. 6 years passed before he was assigned his first mission. 6 years of training, preparation, and hope. When Challenger left the launch pad, Smith finally achieved what he had spent years pursuing. His first space flight lasted 73 seconds. Years after the disaster, investigators discovered that several personal emergency air packs inside the cabin had been manually activated. Smith's was among them. The detail raised the possibility that at least some members of the crew may have remained alive for a short time after the vehicle broke apart. No one knows exactly what happened during those final moments. That uncertainty makes the story heavier. If Michael Smith represented patience, Judith Resnick and Ronald McNair represented the pursuit of knowledge. Judith Resnick was an exceptional electrical engineer. She held a doctorate and had worked in demanding research environments that required a very high level of expertise. After joining NASA, she quickly became one of the most prominent members of a new generation of astronauts. She was also the second American woman to fly in space. Resnick was not easily swept away by public relations slogans. When the Teacher in Space program was announced, she initially had doubts. She worried that placing a teacher on the mission might overshadow its scientific objectives. But after months of training alongside Krista McAuliffe, her view changed. She realized that inspiration had its own value. Ronald McNair followed a very different path. He grew up in South Carolina during a time when racial segregation still shaped much of American life. As a child, he was once denied permission to borrow a book from a whites-only library. He did not leave. Eventually, he was allowed to check out the book he wanted. That small moment seemed to foreshadow the rest of his life. McNair kept moving forward, no matter how many doors were closed in front of him. He earned a doctorate in physics from MIT and later became an internationally recognized laser scientist. Among the items he planned to carry aboard Challenger was something unusual: his saxophone. McNair intended to record the first performance in space by a professional saxophonist. One dedicated his life to electrical engineering, the other to laser physics. Both boarded Challenger, believing that space could expand the limits of human understanding. The shuttle also carried very different dreams. Ellison Onizuka grew up in a coffee farming family in Hawaii. From fields on a remote island in the Pacific, he became the first Asian American to travel into space. Before launch day, he called his family. Relatives later recalled that it was not something he normally did. Elsewhere inside the crew cabin sat Gregory Jarvis. He was an engineer focused on fluid dynamics in zero gravity. His work was not glamorous. It was aimed at gathering data that could help design future satellite systems. Jarvis had waited nearly 2 years for a seat aboard Challenger. On multiple occasions, His position had been reassigned to individuals with greater political value or media appeal. It was a striking contradiction. A program that consistently declared science its highest priority repeatedly postponed a scientist in order to serve other objectives. The final person in the photograph was Christa McAuliffe. She was not a pilot, not an engineer, not a scientist. She was a high school teacher of history and civics from New Hampshire. Out of more than 11,000 teachers who entered the nationwide selection process, she was chosen. Her mission was not to conduct a complex experiment. She had been given a task that was simpler, yet far more influential. Teaching from orbit. Christa planned to deliver 2 live lessons from space. She would introduce students to daily life aboard the shuttle and explain why the space program mattered to education. Back at her school in Concord, students were ready. Large screens had been installed. They were waiting to see their teacher from beyond Earth. A teacher was preparing to begin the biggest lesson of her life. The nation was preparing to witness the opposite. On the morning of January 28, 1986, all 7 crew members put on the same flight suit and left the operations and checkout building at Kennedy Space Center. Dick Scobie walked in front. The others followed behind. They smiled, talked, and greeted the people standing along the pathway. Christa McAuliffe waved repeatedly toward the cameras pointed in her direction. It was an unusually cold morning for Florida. What they did not know was that only hours earlier, intense debates had still been taking place. Engineers were trying to stop the launch. Warnings had been raised about the temperature. Recommendations had been made to delay the mission. The people who built the rocket were trying to prevent the flight. The people sitting on top of the rocket never knew. What killed Challenger was not an explosion, at least not at first. It began with something much smaller, a rubber seal, small enough to be held between 2 fingers. When Challenger lifted off on the morning of January 28, 1986, most of the public's attention was focused on the white orbiter attached to the massive orange external fuel tank. It was the most visible part of the system, but the real force pulling Challenger away from Earth was mounted on either side of the vehicle. Those were the solid rocket boosters, commonly known as SRBs. Each booster stood more than 45 meters tall, measured roughly 3.7 meters in diameter, and weighed approximately 580 tons when fully loaded with propellant. During the first 2 minutes of flight, nearly all of the shuttle's power came from these 2 enormous steel cylinders. Around 83% of the thrust that carried Challenger into the sky was generated by them. Without the SRBs, the space shuttle would not have left the launch pad by even a single meter. From the outside, they appeared to be solid steel structures. In reality, they were not. Because of their enormous size, the boosters were manufactured in separate sections in Utah before being transported by rail to Florida. Only after arriving at Kennedy Space Center were these cylindrical segments assembled into a complete rocket. Those joints would become the weakest link in the entire story. Inside the boosters, propellant burned at temperatures exceeding 2,700 degrees Celsius. The pressure produced was powerful enough to lift a system weighing thousands of tons off the ground. Between that extreme environment and the outside air stood only a very small line of defense. In practical terms, just 2 rubber seals. Each field joint contained two separate O-rings, a primary seal and a backup seal. Their job sounded simple. They had to prevent hot gases from escaping the rocket casing. They had to stop burning gases from finding their way through the gaps between metal sections. The moment the propellant ignited, internal pressure rose almost instantly. Steel components expanded and flexed slightly under the enormous load. That movement created microscopic gaps at the joints. That was the critical moment. The O-ring had to respond almost immediately. It had to expand and seal the newly formed gap before hot gases could find a path through it. It sounds like an insignificant detail, but the safety of the entire system did not depend on the thickness of the steel or the power of the engines. It depended on the reaction speed of a rubber ring small enough to fit comfortably in the palm of a hand. A machine designed to carry human beings into space was being protected by something so small that most people would never notice it if it were lying on a desk. And at that point, temperature became the most dangerous enemy of all. The O-ring was made from a synthetic rubber compound. Its greatest strength was not hardness, but flexibility. It needed to be elastic enough to deform under pressure and then quickly return to its original shape. That ability allowed it to seal gaps in a fraction of a second. But rubber has an inherent weakness. As temperatures fall, the molecules inside become stiffer. Elasticity decreases. Recovery after compression becomes significantly slower. Years of testing had revealed a troubling pattern. The colder it became, the slower the O-ring responded. Under ordinary circumstances, that might have been a minor difference. Inside a rocket booster, it was the difference between safety and disaster. A seal might take several seconds to recover the shape needed to close a gap. The hot gases inside the rocket did not need several seconds. They needed only a tiny fraction of one. Rubber was reacting on the scale of seconds. Flame was reacting on the scale of milliseconds. On the morning of January 28, 1986, that difference became especially frightening. Temperatures at Cape Canaveral fell close to freezing. Ice formed on multiple structures around the launch complex. Engineers observed weather conditions colder than any previous space shuttle launch. Even more concerning, the aft field joint on the right booster was estimated to be significantly colder than anything the system had previously experienced. No one possessed real flight data showing how the O-rings would behave under such cold conditions at ignition. It was uncharted territory. A component known to be highly sensitive to temperature was about to face the coldest environment in the history of the program. Yet the decision to launch remained unchanged. What makes this detail so serious is not ignorance. It is the fact that the warning signs had appeared long before that morning. In November 1981, after Columbia's STS-2 mission, engineers discovered signs of O-ring erosion on a recovered booster. The damage indicated that hot gases had partially breached the sealing system. According to the original design, that was never supposed to happen. The anomaly was documented. Reports were written. Discussions took place. The program continued. Over the following years, more flights revealed similar evidence. Erosion, signs of hot gas blow by. Reduced sealing performance. A dangerous pattern began to emerge. Each time an anomaly appeared, the shuttle returned safely. Each time the shuttle returned safely, concern faded a little more. Gradually, what had once been considered abnormal began to be accepted as part of normal operations. the risk never disappeared. People simply became more familiar with it. By January 1985, the STS-51C mission flew in the coldest launch conditions experienced up to that point. After the boosters were recovered and inspected, engineers found the most severe O-ring erosion ever recorded. The connection between low temperatures and declining O-ring performance was becoming increasingly difficult to ignore. It was no longer speculation. It was real data collected from actual flights. The paradox was that as the evidence grew stronger, so did the pressure to keep the shuttle schedule moving. The warning signs became familiar. Repeated cautions gradually lost their weight. Buried inside technical charts, post-flight analyses, and the small burn marks appearing on rubber seals. One man was seeing a conclusion that many others did not want to face. His name was Boisjoly. He believed what was happening was not a random occurrence. It was a warning. And if the system failed to change, a day would come when that warning would no longer appear on rubber. It would appear on a list of the dead. Roger Mark Boisjoly was born in Massachusetts in 1938. A veteran aerospace mechanical engineer, he spent years working for Morton Thiokol in Brigham City, Utah. Within the vast machinery of the space shuttle program, he was not a senior executive. He was not a public spokesperson for NASA. Outside engineering circles, his name was virtually unknown. Boisjoly's work focused on a small component buried deep inside the solid rocket boosters. Specifically, he worked on the field joints, where sections of the booster were connected and sealed by a system that relied on rubber O-rings. It was not the kind of job that brought recognition, but it demanded an intimate understanding of how those joints behaved under enormous pressure, extreme temperatures, and violent vibration during launch. Boisjoly understood that system better than almost anyone. He worked with data. He trusted numbers. In his world, physics had no interest in launch schedules. Pressure did not care about press conferences. Temperature did not change simply because an agency was facing political pressure, while the people making final decisions were often thousands of miles away from the launch pad. The person who saw the danger most clearly was sitting in an office in Utah. An early winter flight in 1985 led him to suspect that the system was hiding a problem far more serious than it appeared. In January 1985, mission STS-51C launched in the coldest conditions the shuttle program had experienced up to that point. After the mission, the solid rocket boosters were recovered from the Atlantic Ocean for inspection. Boisjoly participated in the evaluation of the field joints and the O-rings inside them. What he saw was difficult to ignore. The erosion on the O-rings was significantly worse than on previous flights. Evidence that hot gases had breached the sealing system was becoming increasingly clear. That meant the final barrier between the superheated combustion gases and the booster wall had not performed as originally intended. Many people might have viewed it as an isolated technical defect. Boisjoly saw something else. He saw a pattern taking shape. The colder it became, the slower the O-rings responded. The colder it became, the weaker the seal. The colder it became, the greater the chance that hot gases could slip past the protective barrier. This was no longer a series of random incidents. It was evidence of cause and effect. From that point on, he began gathering data systematically. Throughout the first months of 1985, Boisjoly reviewed records from previous missions. He compared launch temperatures against the level of O-ring damage observed after booster recovery. The results grew increasingly troubling. There had not been a single low-temperature flight in which the seals remained completely intact. Missions launched under colder conditions consistently showed greater erosion. One particularly important detail began to emerge. No shuttle mission had ever launched at temperatures below roughly 53 degrees Fahrenheit, about 12 degrees Celsius. In other words, the entire program had never truly tested the O-rings below that threshold. Many people might have considered the lack of data an insignificant gap. An engineer understood the opposite. A lack of data does not mean safety. Sometimes the absence of data is the strongest warning of all. In the summer of 1985, Boisjoly decided to put those concerns in writing and elevate them to management. On July 31, 1985, he sent a memorandum to Robert Lund, Morten Thiokkol's Vice President of Engineering. The message was anything but vague. Boisjoly warned that O-ring erosion was developing into a serious threat. He recommended creating a dedicated team to investigate and address the issue. The most important part of the memo was how he described the potential consequences. He did not treat it as a routine engineering problem. He warned that if immediate action was not taken, the eventual outcome could be the loss of a vehicle and the loss of human life. 6 months before Challenger exploded, an engineer had already written down the exact kind of disaster he feared. The memo was not completely ignored. Morten Thiokkoll formed an O-ring task force. Boisjoly became part of it. Meetings were held, reports were prepared. Additional data continued to be collected. From the outside, the system appeared to be responding. But responding is not the same as changing. No emergency redesign was immediately implemented. No order was given to halt the program. No missions already in preparation were postponed. The problem had been acknowledged. The solution had not arrived. After weeks of work, Boisjoly began to realize that the task force lacked the authority to create meaningful change. They could identify risks. They could write reports. They could present data, but they did not control the schedule. By late 1985, pressure on the shuttle program was increasing. More missions were being added to the manifest. Challenger had been assigned a special role as the carrier of the Teacher in Space program. Public attention continued to grow. Against that backdrop, Boisjoly repeatedly raised concerns about the connection between low temperatures and O-ring failure during technical meetings. The closer the year came to its end, the less welcome those warnings became. The data called for caution. The system demanded speed. One engineer was trying to prevent a disaster. An organization was trying to keep its schedule intact. The winter of 1986 arrived just as that conflict reached its breaking point. In the final days of January, weather forecasts showed temperatures at Cape Canaveral could drop to near or below freezing on the night before launch. For most people, it was simply a weather report. For Roger Boisjoly, it was the one thing he had hoped never to see. Everything he had spent the previous year documenting pointed to the same conclusion. O-rings performed worse as temperatures fell. Now the system was preparing to place them in conditions that had never been tested. He did not see a forecast. He saw an experiment that would be conducted in the real world, an experiment with 7 people inside the spacecraft. NASA saw a launch date. Roger Boisjoly saw the possibility of death. On the evening of January 27th, 1986, telephones began ringing between Utah, Alabama, Texas, and Florida. On one end of the line were engineers trying to stop the flight. On the other were people responsible for protecting the shuttle program's schedule. The meeting lasted less than 3 hours. The decision was made in less time than it takes to watch a movie. Its consequences would endure for decades. At approximately 8:45 p.m. on January 27, 1986, a conference call connected 3 locations separated by thousands of miles. In Florida was the Kennedy Space Center, where Challenger stood waiting on the launch pad. In Alabama was the Marshall Space Flight Center, responsible for overseeing the solid rocket booster program. In Brigham City, Utah, sat Morton Thiokol, the company that designed and manufactured those boosters. Everyone on the call understood this was not a routine meeting. Nobody was there to complete paperwork. Nobody had been summoned to provide a project update. The entire discussion revolved around a single question. Should Challenger launch the following morning? Outside the conference rooms, temperatures in Florida continued to fall. Weather forecasts showed that the morning of January 28th would be unusually cold. The numbers appearing on meteorological reports were making many Morton Thiokol engineers uneasy. They were not worried about the schedule. They were not worried about the program's reputation. They were worried about a small component buried deep inside a booster joint, a rubber seal called an O-ring. For Roger Boisjoly, Arnie Thompson, and several other engineers, the answer to the evening's question had already been decided before the phone lines were connected. Do not launch. Before the meeting began, the engineering team had prepared 13 data slides. The documents were faxed to Florida and Alabama, so all parties could review the same information. These were not opinions. They were years of real flight data. Boisjoly and Thompson took turns presenting their analysis. Forecasts indicated that launch morning temperatures could range from about -3 to -1 degrees Celsius. That would place Challenger in conditions far colder than any previous shuttle launch. The coldest shuttle mission to date had launched at roughly 11 to 12 degrees Celsius. The difference between those temperatures was not a few degrees. It was an entirely untested region. The engineers continued presenting data related to the O-rings. Flights conducted in colder weather consistently showed more severe erosion of the seals. As temperatures dropped, damage increased. The pattern appeared again and again across multiple inspections. One detail is particularly important. The engineers were not claiming with certainty that Challenger would explode. They were saying the opposite. There was no data proving that the O-rings would remain safe at the temperatures expected the next morning. Every piece of existing evidence pointed in the opposite direction. This was no longer a debate about performance. It was a debate about whether the booster could maintain pressure containment. If the O-ring failed to seal the joint at the critical moment, combustion gases reaching thousands of degrees could breach the barrier. If that happened, the consequences would extend far beyond a damaged component. The lives of 7 people would be at stake. After the presentation, Robert Lund spoke. As Morton Thiokol's Vice President of Engineering, he was the highest technical authority in the meeting. Lund did not challenge his engineers. In fact, he agreed with them completely. He stated that he couldn't recommend launch if temperatures fell below roughly 12 degrees Celsius. This was not a personal opinion. It was the official position of the engineering department. Based on that position, Morton Thiokol delivered its recommendation to NASA. Do not launch. The moment created a striking contrast. The company that built the boosters had just recommended stopping the mission. Meanwhile, NASA was only hours away from launch. The response came almost immediately. Lawrence Malloy, NASA's manager for the Solid Rocket Booster program, rejected the conclusion. Rather than focusing on whether the system had been proven safe, he asked Thiokol to provide evidence that the boosters would definitely fail. That became the turning point of the entire meeting. The engineers were operating under a principle deeply rooted in aerospace. If safety has not been demonstrated, you do not fly. Some program managers approached the issue differently. If danger has not been proven beyond doubt, you can still fly. The difference sounds subtle. In reality, it completely reversed the burden of proof. As tensions rose, Malloy asked a question that would later become infamous. In essence, he wanted to know when they expected to launch if they continued delaying missions like this. It was not a technical argument. It was a sign that schedule pressure had entered a discussion that should have been governed solely by data. George Hardy at Marshall reacted strongly as well. He stated that he was astonished by Thiokol's recommendation not to launch. No direct order was given. Nobody explicitly told the engineers to change their position. Yet the message was unmistakable. NASA was unhappy with the answer it had received. The meeting was beginning to move out of the realm of engineering and into the realm of power. Shortly after 10:00 p.m., Joe Kilminster requested a pause so Morton Thiokol could hold an internal discussion. The break was expected to last only a few minutes. It stretched to nearly half an hour. Inside the conference room in Utah, the atmosphere grew heavy. Boisjoly and the other engineers continued defending the data. They returned to the temperature charts, the photographs of O-ring erosion, and reports from previous flights. None of them changed their position. What began to change was management. New questions emerged. What would happen if they continued refusing NASA? What would happen to the relationship between contractor and customer? What would happen to the program if another mission was delayed? Then came a statement that would later become symbolic of the entire Challenger tragedy. Gerald Mason suggested that Robert Lund should take off his engineering hat and put on his management hat. In a brief moment, the focus of the meeting shifted completely. It was no longer about physics. It was no longer about temperature. It was no longer about O-rings. It was no longer about data. The focus was now program management. Boisjoly continued to object. He pointed to the damaged photographs. He repeated the connection between low temperatures and O-ring failure. He tried to steer the discussion back to the evidence. Nobody asked for additional analysis. Nobody suggested gathering more information. Nobody raised further questions about the erosion images. Years later, Boisjoly described his feeling with a single word: helpless. What makes the story remarkable is that the data had not changed since the beginning of the meeting. Only the decision was changing. Afterward, Thiokol's senior managers met privately. No formal engineering vote was conducted. No collective opinion was taken from the full engineering team. The final outcome was a reversal of the original recommendation. Do not launch became recommend launch. That is the center of the entire tragedy. The people who understood the O-rings best objected. The people signing the final decision approved it. The data did not change. The temperature did not change. The O-rings did not change. Only the signatures changed. Joe Kilminster signed the revised recommendation and faxed it to Kennedy Space Center. Morton Thiokol officially recommended proceeding with mission STS-51L. NASA accepted the recommendation almost immediately. There was no request for additional review, no second round of evaluation. The final barrier standing between Challenger and launch disappeared. Not everyone agreed with the decision. In Florida, Alan MacDonald refused to sign the approval document. As Thiokol's representative at Kennedy, he believed the technical evidence did not support the decision that had just been made. Years later, he explained that if the worst happened, he did not want to explain why he had agreed. His refusal revealed something important. Even within Thiokol's management ranks, true consensus did not exist. Near midnight on January 27, 1986, Roger Boisjoly left the meeting with the feeling that a serious mistake had just been made. In Florida, launch preparations continued. Outside on the pad, temperatures kept falling. Ice began forming on various structures around the launch tower. The engineers had failed to stop the flight, but Challenger was still on the ground. The last opportunity to reverse the decision still existed. During the early hours of January 28th, Florida became even colder than many forecasts had predicted. Ice coated the launch tower like a physical reminder of the debate that had taken place the night before. The engineers saw what they feared. The managers saw what they had accepted. By the time the sun began rising over the horizon, the argument had been over for hours. No one was trying to stop the launch anymore. The night of January 27th, 1986 ended with a decision. Hours of debate between engineers and management had finally come to a close. The launch remained on schedule. On paper, the issue had been resolved. Outside, the weather had no interest in meeting minutes. Temperatures continued to fall as darkness settled over the Kennedy Space Center. At launch pad 39B, cold air swept through the massive steel structures of the launch complex. In some areas, temperatures dropped below freezing. It was the coldest launch eve ever recorded in the history of the Space Shuttle program. Ground crews kept water flowing through pipes to prevent them from freezing. Yet that solution created a new problem of its own. When the water met the unusually cold air, it quickly turned to ice across the metal surfaces of the launch tower. Inside the operations offices, the technical debate had ended. Out at the pad, nature continued delivering its final warnings. Before sunrise, another team began noticing something that had never appeared on previous missions. An ice inspection crew was dispatched to launch pad 39B. What they found caused immediate concern. Ice had formed at multiple locations across the tower. Some icicles stretched nearly a foot in length, hanging from steel beams. Elsewhere, large sheets of ice clung tightly to the metal structures. The concern was not how they looked. The concern was what would happen when Challenger lifted off. If those chunks of ice broke loose under vibration and aerodynamic forces, they could strike the shuttle or the external fuel tank at tremendous speed. Technicians climbed the tower in freezing conditions, using hand tools. They chipped away ice, one section at a time. The work was slow, careful, and lasted for hours. None of this was normal. No one could find comparable images from previous launches. What made it remarkable was that the ice was visible to everyone. The O-rings, meanwhile, were buried deep inside the solid rocket boosters. No one standing at the launch site could see them with the naked eye. The visible warnings were everywhere. The invisible warning remained hidden from view. That morning, the most important people in the story still had no idea what had happened during the previous night's heated debate. Inside the crew quarters, the 7 astronauts woke according to schedule. Dick Scobie, Michael Smith, Judith Resnick, Ronald McNair, Ellison Onizuka, Gregory Jarvis, and Krista McAuliffe shared breakfast, completed their final medical checks, and prepared to suit up. None of them had attended the meeting the night before. None of them had heard the original recommendation that the mission should be delayed. None of them knew about the arguments surrounding the ability of the O-rings to seal properly in cold weather. That was how the system worked. The crew was not asked to make the final assessment of technical risk. They received a conclusion from the system. They trusted that conclusion. The debates that produced it never reached the cockpit. A cold paradox emerged that morning. The people who would ride the shuttle knew nothing about the argument. The people who understood the argument best would never have to board it. Among the 7 crew members, one person drew particular attention from the American public. Krista McAuliffe was not a test pilot. She did not come from a military background. She was a high school teacher from Concord, New Hampshire. The Teacher in Space program had transformed her into the public face of STS-50 Binonel. That morning, she gave interviews, posed for photographs with reporters, and prepared for the first classroom lessons that would be broadcast from orbit. Those who saw her remembered a woman who appeared cheerful, relaxed, and constantly smiling at the people around her. For millions of Americans, this was not simply another NASA flight. It was the flight of an ordinary citizen, invited into a world usually reserved for professional astronauts. Another contrast emerged. The most famous person on board was also the one with the least experience living with the occupational risks of aerospace flight. Meanwhile, the astronauts' families began gathering at the viewing area reserved for invited guests. Many noticed the unusually cold weather. Some noticed traces of ice still visible on parts of the launch tower. They could see the outward signs of an unusual morning. What they couldn't see was what had happened behind the closed doors of the meeting rooms. Dick Scobie spoke with family members before launch. He reassured them that everything was fine. Their loved ones could only see the surface of the event. They had no access to the technical arguments behind it. People outside the system could see the ice. People inside the system could see the data. Neither group had the power to change a decision that had already been made hours earlier. Challenger still could not launch on schedule. From around 7 o'clock in the morning until nearly noon, a series of delays pushed the countdown back. A fault in the fire detection monitoring system required technical teams to troubleshoot the issue before the countdown could continue. At 8:03 a.m., the crew began boarding the spacecraft. By 8:36 a.m., all 7 astronauts were strapped into their seats. Meanwhile, the ice inspection teams continued their work. NASA personnel repeatedly reviewed the safety conditions. What is worth reflecting on is that every delay that morning involved something that could be directly seen or measured. Not a single delay involved the O-rings. The visible problems were inspected again and again. The most dangerous problem remained hidden in the one place nobody could observe. More than 2,000 miles away from Kennedy, Roger Boisjoly was beginning the longest morning of his life. Back in Utah, there were no more meetings to attend, no more arguments to make. The decision had already been made. He knew the actual temperatures were far lower than the conditions his engineering team had previously evaluated. He knew the O-rings were about to enter a range of operation that had never been tested. But there was no new data. There was no new opportunity to change the outcome. There was only time, moving minute by minute toward launch. It was the moment when the engineer lost all control over the system. He understood better than anyone else. At 11:38 a.m., on January 28, 1986, the countdown reached its final number. The three main engines ignited. Then came the two solid rocket boosters. Challenger left the launch pad. Families waved. School children cheered in front of television screens. Networks broadcast the launch live to millions. No one could see what was happening inside the right solid rocket booster. Less than a second after liftoff, at approximately 0.678 seconds into the flight, a puff of gray smoke appeared at the aft field joint of the right booster. The primary O-ring had failed to create a complete seal as pressure rapidly increased. A temporary phenomenon followed. Combustion byproducts from the propellant briefly filled the gap, acting like an improvised patch that appeared at exactly the right moment. That was the most frightening detail in the entire disaster. Challenger did not rise because the system was functioning as designed. Challenger rose because something outside the design temporarily concealed the design failure. For nearly the next minute, everything looked perfectly normal. The astronauts did not know. NASA did not know. The audience did not know. But the flight had begun to fail from its very first second. For the next 58 seconds, Challenger continued climbing into the sky just as countless missions before it had done. Then the upper-level winds arrived. The temporary seal began to weaken. The clock kept running, and it was moving steadily toward the number that would be remembered forever. 73 seconds. (11:38 a.m., January 28, 1986. At Launchpad 39B in Cape Canaveral, Challenger began its 10th mission. Thousands watched from viewing areas around the Space Center. Hundreds of thousands of schoolchildren followed along on live television. For most people present that day, this looked like an ordinary shuttle launch. At T+0 seconds, the two solid rocket boosters ignited. Challenger rose from the ground in the familiar column of fire that had become the signature of the Space Shuttle program. Everything unfolded exactly as expected, but less than a second later, at approximately T+0.678 seconds, high-speed cameras captured a detail that nobody noticed at the time. Several puffs of gray smoke appeared near the aft field joint of the right solid rocket booster. It was the first visible sign that the O-ring had failed to do its job. Inside the booster, pressure climbed almost instantly, exceeding 900 psi. Extremely hot combustion gases began searching for a path through the gap in the joint. By design, the O-rings were supposed to prevent this from happening. On that freezing morning, they did not. What is remarkable is that Challenger did not explode. The system did not collapse immediately. Instead, a random event intervened. Molten aluminum oxide particles produced during the combustion of the solid propellant were swept into the gap. By chance, they formed a temporary seal, like an improvised patch created in the middle of chaos. At this point, the system was no longer functioning as designed. It was being held together by luck. Inside the cockpit, Dick Scobie and Michael Smith continued standard flight procedures. There were no warning lights, no alarms, no indication whatsoever that one of the most critical components in the entire system had failed within the first second of flight. The physical data was telling one story. The outward appearance was telling another. For the first 36 seconds, Challenger looked perfect. As the shuttle continued climbing, the environment around it began to change. At approximately T plus 36 seconds, Challenger entered a region of strong upper-level wind shear. These winds were more intense than expected. The onboard guidance system continuously adjusted the vehicle's attitude to maintain a stable flight path. Between T plus 45 and T plus 50 seconds, aerodynamic loads increased rapidly. The entire structure vibrated and flexed within its design limits. That was normal for a vehicle accelerating through the atmosphere at tremendous speed. At the joint of the right booster, however, those vibrations produced a different result. The aluminum oxide deposit that had temporarily sealed the gap began to crack. The joint shifted. The final layer of protection, created entirely by chance, was losing its integrity. The irony was that Challenger continued flying beautifully. The shuttle's sophisticated control systems successfully handled the challenging aerodynamic conditions. At the same time, that very success allowed the vehicle to survive long enough to move closer to disaster. By the 58th second, the last of the luck ran out. At approximately T plus 788 seconds, the temporary seal failed completely. A jet of flame nearly 3,000 degrees Celsius burst sideways from the right booster. It was not large. It did not produce an explosion. It attracted no attention from anyone on the ground. Viewed in isolation, it looked little different from an exceptionally powerful industrial blowtorch. The terrifying part was not the size of the flame. The terrifying part was where it was pointing. The jet was aimed directly at the strut, connecting the booster to the external tank, and toward the area containing liquid hydrogen. It was one of the most critical locations in the entire launch system. Nobody on the ground noticed. Nobody in the cockpit received a warning. No abnormal indication appeared inside mission control. A flame far smaller than the shuttle's main engines was quietly preparing to destroy a machine worth billions of dollars. After T plus 60 seconds, the flame continued burning into the attachment structure. By approximately T plus 64 seconds, sensors began recording a drop in pressure inside the right booster. Combustion gases were escaping. Between T plus 66 and T plus 70 seconds, the flame penetrated the insulation and began attacking the outer wall of the liquid hydrogen tank. On one side was a stream of combustion gases approaching 3,000 degrees Celsius. On the other side were liquid hydrogen at approximately minus 253 degrees Celsius and liquid oxygen at approximately minus 183 degrees Celsius. This extreme physical contrast caused the metal structure to weaken at an accelerating rate. Nobody knew that the entire system was now only seconds away from collapse. At approximately T plus 72 seconds, the lower attachment strut between the right booster and the external tank failed completely. The booster lost its lower anchor point. It began pivoting around the upper attachment point like a giant door suddenly torn free from its bottom hinge. The nose of the booster struck the upper liquid oxygen tank. The structural integrity of the oxygen tank began to fail. Inside the cockpit, flight recorder data suggests that Michael Smith may have uttered two brief words. "Oh." They are widely regarded as the last recorded words from the flight. Less than 2 seconds later, Challenger disappeared. At T plus 73.62 seconds, at an altitude of roughly 14 to 15 kilometers and traveling at nearly Mach 1.92, the liquid hydrogen tank ruptured first. The liquid oxygen tank failed moments later. The propellants mixed almost instantly, creating the enormous fireball that would become one of the most recognizable images in modern history. For years, the public described Challenger as having exploded. The reality was more complicated. The orbiter did not detonate like a bomb. The fuel system was destroyed. Massive aerodynamic forces struck a vehicle that was rapidly losing structural stability and tore it apart. Orbiter Challenger disintegrated. The crew cabin separated from the rest of the vehicle. The two solid rocket boosters continued flying for a short time before being destroyed by remote command. Across the Florida sky, a giant white Y-shaped cloud spread outward. The image quickly became one of the most painful symbols of the 20th century. The worst disaster in NASA's history had begun with a component that cost only a few dollars. Inside Mission Control, Challenger's data disappeared from the screens. Radar lost the target. Engineers stared at streams of numbers that had suddenly stopped updating. Then a voice broke the silence. Struggling to remain composed in a situation nobody had ever experienced before. Flight controllers here, looking very carefully at the situation. Obviously a major malfunction. In the viewing stands, many people continued staring at the sky. Some still did not understand what had happened. June Scobie initially thought it might be some kind of unusual stage separation event. Only minutes later did the reality begin to emerge. In classrooms across America, hundreds of thousands of students remained fixed on their television screens. Many teachers had no idea what to say. In a matter of seconds, a highly anticipated scientific milestone had become a national tragedy. NASA quickly announced that the entire crew had been lost. But discoveries made afterward raised a question even more unsettling than the fireball over Florida. Several emergency oxygen systems had been activated. That finding led to the most haunting question of the entire Challenger disaster. Was anyone inside the crew cabin still alive after the 73rd second? From early February through mid-March 1986, a massive search operation unfolded off the coast of Cape Canaveral. While millions of people remained haunted by the image of a fireball tearing across the Florida sky, the real work of the investigation was only beginning. U.S. Navy ships, rescue divers, salvage specialists, and investigative teams were deployed continuously into the Atlantic Ocean. The greatest challenge was that Challenger had not fallen into the sea as a single intact object. When the vehicle broke apart at high altitude, thousands of fragments were scattered across an area covering hundreds of square kilometers. Ocean currents constantly shifted the debris field, making the recovery effort extraordinarily difficult. For weeks, investigators recovered little more than twisted metal, bent structural components, and fragments of the shuttle system. The breakthrough came in early March. Navy sonar detected a large structure resting on the ocean floor. When the recovery team reached the site, they realized they had found the crew cabin, the very compartment that had carried all 7 members of mission STS-51L. The discovery immediately changed the direction of the investigation. The cabin was severely deformed. Structural frames had been crushed by an enormous impact force. Yet what stunned investigators was that it had not been destroyed during the breakup in the sky, as many had assumed. The crew cabin had survived the fireball. If the cabin had not been destroyed when Challenger disintegrated, a new question emerged. What happened to the people inside? The first clues came from several small objects found among the wreckage. Each crew member carried an emergency device known as a beep. It was a personal air supply system intended for use during a cabin emergency. The unit did not activate automatically. It had to be switched on manually by the wearer. When specialists examined the recovered devices, they discovered that 3 beep units had been activated. Another showed signs of having been handled. Investigators could not determine exactly who had activated them. The remaining evidence was insufficient to reconstruct every action inside the cabin. However, one airbag assigned to Michael Smith was confirmed to have been turned on. That detail carried enormous significance. It showed that at least some crew members were still capable of taking action after Challenger broke apart at T+73 seconds. That much is known. Everything beyond that remains uncertain. How long they remained conscious, whether they spoke to one another, whether they understood that the shuttle no longer existed, or whether they were simply reacting instinctively to an unfolding emergency. For years, the public often heard that death occurred instantly when Challenger exploded. The investigation revealed a far more complicated picture. Activating an airbag was not the same thing as surviving. Another critical question quickly emerged. Did the cabin lose pressure immediately after the breakup? To evaluate the crew's chances of survival, a team of biomedical experts was tasked with analyzing every piece of remaining evidence. Their final conclusion was remarkably cautious. The available evidence did not allow investigators to determine whether the crew remained conscious after the vehicle broke apart. It became one of the most famous conclusions of the entire investigation. 2 possibilities existed side by side. The first was that the cabin lost pressure almost immediately. If that happened, oxygen deprivation at high altitude could have rendered the crew unconscious within seconds. The second was that the cabin retained at least part of its pressure after separating from the rest of the shuttle. In that case, some crew members might have remained conscious for a longer period. No one knows which is true. Challenger carried no cockpit voice recorder. It had no black box equivalent to those used in commercial aviation. There was no final conversation, no audio recording, no witness. That void remains to this day. NASA has never claimed that the crew lost consciousness immediately. At the same time, it has never claimed that they remained conscious until impact. Between those 2 possibilities lies a darkness no one can enter. There is only one thing that is absolutely certain. The crew cabin continued to exist after Challenger ceased to exist. At an altitude of roughly 14 to 15 kilometers, the cabin became an independent object following a ballistic trajectory. During the first few moments, momentum carried it upward for a short distance. Then gravity took over. The cabin began its descent toward the Atlantic. The entire process lasted approximately 2 minutes and 45 seconds. A cold fact emerges when the numbers are placed side by side. Challenger survived 73 seconds after leaving the launch pad. The crew cabin survived nearly 3 minutes after Challenger itself was gone. That final span of time lasted longer than the entire flight before the disaster occurred. The last moments did not happen in the sky. They happened on the ocean, when the crew cabin struck the Atlantic at a speed exceeding 300 kilometers per hour. The impact generated forces far beyond the limits the human body can endure. Experts concluded there was no possibility of surviving that collision. The exact moment of death can never be determined with complete certainty. Yet the impact with the water was a fatal event beyond question. The most painful questions are the ones that can never be answered. Was anyone still conscious as the cabin fell? Did anyone see the ocean rushing up toward them? Did anyone fully understand what was happening during those final seconds? No one knows. Perhaps no one ever will. But by this point, the most important question no longer lies inside the cabin. The real question lies outside it. Who brought those 7 people to that moment? Challenger did not fail because the physics was too complicated. The people who designed and operated the system had understood its vulnerability for months before launch. The warnings had been written. The data had been presented. The meetings had been held. The problem was not a lack of information. The problem was a lack of willingness to act on that information. The 7 people aboard Challenger did not walk into an unexpected accident. They walked into a decision that had been signed months earlier. After the disaster, NASA tried to explain it as an unforeseeable accident. Then a physicist appeared. He was not a rocket engineer, not a NASA manager, not a politician. He arrived carrying nothing more than a glass of ice water and a piece of rubber. 30 seconds later, NASA's official story began to collapse. On February 6, 1986, 9 days after Space Shuttle Challenger disintegrated over the skies of Florida, Washington, D.C. entered a different phase of the tragedy. The explosion was already over. Debris was still being recovered from the Atlantic. Every evening, television screens replayed the haunting image of the white Y-shaped cloud hanging in the sky. America was no longer asking what had happened. The question now was who had allowed it to happen. Public trust in NASA collapsed almost as quickly as the shuttle itself. For years, the agency had stood as a symbol of technical excellence, scientific ambition, and humanity's ability to achieve the seemingly impossible. In 73 seconds, that symbol came crashing back to Earth. President Ronald Reagan signed an executive order establishing a presidential commission to investigate the disaster. The man chosen to lead it was William B. Rogers, a former U.S. Secretary of State. Around him sat an extraordinary collection of names. Neil Armstrong, the first human to walk on the moon, Sally Ride, America's pioneering female astronaut, Chuck Yeager, an aviation legend, Donald Kutina, an Air Force general with deep expertise in missile technology, and Richard Feynman, the Nobel Prize-winning physicist, famous for seeing through assumptions that others accepted without question. On paper, the mission of the Rogers Commission was simple: find the cause of the Challenger disaster. In reality, it was far more complicated. NASA was not merely a government agency. It was a national symbol. It was a source of pride inherited from the Apollo era. It was part of the image America projected to the world. An investigation had to uncover the truth. It also was not supposed to completely destroy that symbol. That contradiction existed from the very first day. Within minutes of the opening session, it was almost spoken aloud. William Rogers stated that the investigation should not unfairly damage NASA. He emphasized his personal belief that the agency had done an excellent job for many years. It sounded reasonable. But in an accident investigation, seemingly harmless statements often carry deeper meaning. An investigation can only be truly objective if the conclusion does not exist before the evidence. If the person leading the inquiry publicly declares faith in the organization under investigation, a natural question follows. Will the evidence guide the conclusion, or will the conclusion select the evidence? Some members did not react. Others understood exactly what had just been said. No one was more sensitive to that signal than Richard Feynman. He had not come to Washington to protect NASA's reputation. He had come to discover where physics had been ignored. Feynman was different from almost everyone else in the room. He was a professor at Caltech, one of the most brilliant scientific minds of the 20th century, a man who had spent his career pursuing laws of nature that couldn't be negotiated with. At the time he joined the commission, he was already battling advanced cancer. At first, he did not want the assignment. Experience had made him skeptical of government commissions. Too many investigations existed to manage damage rather than uncover truth. What changed his mind was a feeling he could not shake. Challenger did not look like an ordinary technical accident. Somewhere inside the system, something seemed to be hidden. While many commission members began by reading reports, Feynman chose a different path. He sought out the people who had written those reports. He visited engineering centers. He spoke with engineers at Marshall. He met teams at Johnson. He went directly to contractor offices. He did not ask political questions. He asked simple technical ones. One of them would become famous. In your opinion, what is the probability that a shuttle flight ends in a fatal disaster? The engineers answered almost immediately. Some said 1 in 100, some said 1 in 50, some said 1 in 200. No one believed the system was perfectly safe. No one believed the risk existed only in theory. Then Feynman heard the answer from NASA management: 1 in 100,000. The gap between those numbers was almost unbelievable. One side believed the danger existed in the range of a few percent. The other claimed the risk was nearly zero. This was no longer a disagreement about calculation methods. It was two different worlds, two different realities, two completely different understandings of the same machine. Feynman realized he was no longer investigating a single technical failure. He was investigating a breakdown in perception across an entire organization. During this period, Donald Kutina played a particularly important role. He never publicly attacked NASA, nor could he make sweeping accusations on his own. Instead, he quietly pointed Feynman toward where he should look. Temperature, O-ring, the unusually cold morning of January 28th. That was the trail. The rest belonged to Feynman. He had no intention of proving his case with thousands of pages of paperwork. He wanted to prove it with something anyone could understand. On the evening of February 10th, 1986, in Washington, D.C., Feynman stopped by a hardware store. He bought a small C-clamp and a pair of pliers. No announcement was made. No official demonstration appeared on the hearing agenda. Nobody really knew what he was preparing. Feynman understood a simple principle. A clear image is more powerful than 1,000 pages of explanation. The next morning, that principle changed the entire investigation. On February 11th, 1986, a nationally televised hearing was underway. Millions were watching. On the table sat a glass of ice water. Beside it lay a piece of O-ring material. Feynman used the clamp to compress the rubber. Then he dropped it into the ice water and waited. There was no lengthy speech, no complicated charts, no technical jargon. Just a physicist and a glass of ice water. A few minutes later, he removed the rubber. He squeezed it gently, then released it. The material did not immediately return to its original shape. The deformation remained. The moment lasted less than 30 seconds, but it destroyed months of justification. The physics was remarkably simple. As temperature drops far enough, a material loses a significant amount of its elasticity. The O-ring no longer responds as quickly as the design requires. In the extreme pressure and temperature environment inside a solid rocket booster, that delay can create a deadly gap. That is exactly what happened to Challenger. After finishing the demonstration, Feynman offered only a brief remark. I believe that has some significance for our problem. The sentence was calm. Its weight was enormous. NASA had relied on volumes of documentation. Feynman relied on a glass of ice water. The public understood the issue almost instantly. What worried NASA most, however, was not the demonstration itself. The real concern emerged when the final report was being prepared. Feynman read the draft and was dissatisfied. In his view, it described the technical failure but did not go far enough in explaining the organizational failure behind it. Many wanted the investigation to end with a reassuring message. NASA remained trustworthy. NASA would correct its mistakes. NASA would move forward. Feynman disagreed. He believed that any promise of reform was meaningless unless the systemic causes were described honestly. He was even prepared to remove his name from the report. Eventually, the other members agreed to include his personal statement as an appendix. It became known as Appendix F, only a few pages long, yet perhaps the most famous pages produced by the entire investigation. There, Feynman highlighted the alarming gap between engineering assessments and official claims of reliability. He described the disconnect between the technical level and the management level. He showed how early warnings became diluted as they moved upward through layers of authority. Each management level removed a portion of the uncertainty. Each management level reduced a portion of the concern. By the time the information reached the final decision makers, the danger had been transformed into something acceptable on paper. His closing statement became one of the most famous observations in modern scientific history. For a successful technology, reality must take precedence over public relations, for nature cannot be fooled. It was not merely a conclusion about Challenger. It was a warning to every organization. The moment an institution begins believing the story, It tells the public more than the data provided by its own people. Failure becomes only a matter of time. What Richard Feynman truly exposed was not an O-ring failure. The O-ring was merely the final point of rupture. The failure had begun long before that. It began when engineers raised warnings and were not heard. It continued when managers softened the severity of the risk. It grew when launch schedules became more important than technical data. It reached completion when danger was renamed acceptable risk. The rocket did not explode when the O-ring failed to seal. It exploded the moment an organization began believing that physics could be negotiated. Richard Feynman became the most recognizable face of the investigation, but he was not the first person to speak that truth. There was someone else, an engineer who had been sounding the alarm for months. No one handed him awards. No one invited him onto television. After speaking up, he received what many whistleblowers inside large systems eventually receive: isolation, silence, and, ultimately, the price of saying what the organization did not want to hear. On May 2nd, 1986, more than 3 months after the Challenger disaster, a man walked into a public hearing in Washington, D.C. He was not an astronaut. He was not a politician. He was not a NASA spokesperson. He was Roger Boisjoly. In the months following the disaster, most of the discussion centered on the O-ring, the booster design, and the complex technical details of the failure. The public wanted to know what had broken. Engineers wanted to know which component had failed. But behind all of that remained a much larger question. Who knew about the danger beforehand? And who chose to ignore it? Boisjoly arrived before the Rogers Commission carrying something remarkably simple: internal memos, engineering reports, warnings that had been circulated months before the launch. Most significant among them was a memorandum dated July 31st, 1985. In that document, he and his colleagues had issued a warning in unmistakable terms. If the O-ring problem was not resolved, a mission could be lost. Human lives could be lost. This was not a prediction written after the accident. It was a warning written before it. For the first time, the American public watched an engineer directly involved in risk assessment appear not to explain what had happened, but to demonstrate that it had been foreseen. Silence settled over the room. Yet the most unsettling part was not contained in the stacks of documents on the table. It was what he described next. Boisjoly began reconstructing the meeting held on the evening of January 27th, 1986. The meeting that lasted for hours between Morton Thiokol and NASA on the night before Challenger launched. He spoke of Robert Lund, Gerald Mason, Joe Kilminster, Lawrence Mulloy, George Hardy. He walked through the charts, the temperature data, the arguments. What emerged was very different from the image of an unforeseeable accident. According to his testimony, Thiokol's original engineering position had been clear: do not launch. The engineers concluded that the forecast temperature for the following morning was too low. They had no data proving the O-rings could operate safely under those conditions. In engineering, the absence of evidence for safety does not justify accepting risk. Then the meeting was paused. Thiokol's managers met privately. When the meeting resumed, the original engineering recommendation had vanished. The no-launch recommendation was reversed. Boisjoly explained that what haunted him most was not the final decision itself. It was the logic that produced it. The engineers were asked to prove why the launch should not proceed. The process should have worked in the opposite direction. Management should have been required to prove why the flight was safe enough to launch. The reversal sounds subtle. In reality, it was a reversal of the entire safety principle. When the burden of proof is placed on those raising concerns rather than on those accepting risk, a system begins to lose its ability to protect itself. This was no longer about an O-ring. It was about management thinking. When an organization starts treating warnings as obstacles, the people issuing those warnings eventually become the problem. That moment arrived for Roger Boisjoly far sooner than most people expected. During later hearings, several Thiokol managers presented their own account of the January 27th meeting. In Boisjoly's view, important details had been softened. Some of the pressure coming from NASA was described in terms far less serious than what had actually occurred. He challenged those accounts, not in a private discussion, not in a confidential memo, but before the commission, the press, and television cameras. That was the moment Roger Boisjoly effectively signed his own professional death warrant. To many people, Challenger represented a technical failure. To him, it represented a moral one. One side wanted to identify which part had failed. The other wanted to understand why the warnings had not been heard. From that point forward, Boisjoly was no longer viewed as an internal engineer. He became a whistleblower. In most large organizations, that is a dangerous title. What happened next never appeared in any technical report. There were no charts, no statistics, no investigative appendices. Yet it happens every year in countless companies around the world. After the hearings, Roger Boisjoly remained employed at Morton Thiokol. Officially, reality was different. He slowly disappeared from the company's operating system. Important projects no longer came his way. His name disappeared from major technical meetings. His expertise was no longer sought. Colleagues began keeping their distance. Workplace friendships gradually faded. No one officially declared that he was wrong. No one officially disciplined him. They simply made him invisible. It was an extraordinarily effective form of punishment. The target could point to no termination letter, no disciplinary document. Yet every day brought the unmistakable feeling that he no longer belonged. Alan MacDonald, who had refused to sign the Challenger launch authorization, experienced something similar. He once described the feeling as carrying a taboo that everyone preferred to avoid. Many organizations do not punish by firing people. They punish through isolation. For Roger Boisjoly, the greatest impact was not on his career. It was on his mind. After Challenger, signs of severe stress began to emerge. Persistent insomnia, constant headaches, anxiety, depression, symptoms consistent with PTSD. The tragedy was that he knew he had warned them. He knew he had not made the final decision. He knew the technical record supported him. None of that was enough to silence the questions in his head. Could I have done more? Could I have pushed harder? Could I have gone public sooner? Could I have stopped that flight some other way? The people ultimately responsible sometimes sleep well. The people who tried to prevent the disaster often stay awake for years. By July 1986, his body began to give in. On July 21st, he took medical leave. In September of that same year, Roger Boisjoly left Morton Thiokol. After more than 25 years in aerospace, the career to which he had devoted nearly his entire life came to an end. He never returned to the industry. Amid all that tension, one small detail is often remembered. After one hearing, Sally Ride walked over and hugged him. Years later, Boisjoly recalled the moment with a single sentence. She was the only one. In a system crowded with engineers, managers, and politicians, one of the most human gestures came from an astronaut. But Roger Boisjoly's story did not end with his departure. After receiving psychological treatment, he began appearing in public in a new role. The man who taught the lessons of Challenger from the late 1980s into the early years of the 21st century. He spoke at universities, engineering societies, scientific conferences, and programs devoted to engineering ethics. What stood out was that he rarely began with rockets. He began with responsibility, with organizational pressure, with silence, with professional responsibility, with the price paid when data is ignored in pursuit of other goals. He spoke to hundreds of organizations. His influence extended far beyond aerospace. Many young engineers came to know Roger Boisjoly not because of the O-ring. They knew him as a symbol of professional conscience. Recognition eventually arrived. He received the A.R.S. Award for scientific freedom and responsibility for his courage in defending truth and scientific accountability. NASA reformed its systems. Thiokol redesigned its hardware. Roger Boisjoly spent the remainder of his life helping reshape how an entire generation of engineers thought about ethics. On February 6, 2012, he died after battling multiple forms of cancer. He was 73 years old, a coincidence that many later pointed out. Challenger survived for 73 seconds after leaving the launch pad. Roger Boisjoly lived for 73 years. The man who spent months trying to stop that doomed flight lived longer than the spacecraft by a ratio of 1 year for every second. Many of the people involved in the decision-making process continued their careers. No one faced criminal prosecution. No one went to prison. The person forced to leave the profession he loved was the one who had been right. That may be the saddest paradox in the entire Challenger tragedy. An organization can forgive mistakes, but many organizations never forgive the people who make those mistakes visible. Yet Challenger does not end with Roger Boisjoly. After 73 seconds in the Florida sky, NASA was forced to do what it had postponed for years: stop. For the first time since the Space Shuttle program began, the largest machine in American aerospace fell silent. 32 months, more than 100 engineering changes, a complete reconstruction, a reconstruction that, had it happened sooner, might have saved 7 lives. On January 28, 1986, just 73 seconds after leaving the launch pad in Florida, Challenger disappeared from the sky in front of millions of witnesses. During the first few minutes, many people still did not fully understand what had happened. Television screens continued replaying the image of a massive white cloud against a blue sky. Commentators struggled to explain what viewers were seeing. Families and school children watching the live broadcast continued waiting for confirmation that the crew was safe. That confirmation never came. Only hours after the disaster, one of the most important decisions in NASA's history was made. The entire Space Shuttle program was grounded. At the Kennedy Space Center, at NASA headquarters in Washington, and at research facilities across the United States, plans were immediately frozen. There would be no next launch schedule. No newly approved missions. No public commitments to future flight dates. For years, the Space Shuttle program had been promoted as a revolutionary step forward. It was presented as a spacecraft that could operate routinely, repeatedly, and with increasing efficiency. Yet within a single morning, that entire system became the subject of the largest technical, political, and legal investigations in American aerospace history. The result was a 32-month suspension of shuttle operations. 32 months is a very long time for a national program. During the Cold War, the United States developed several highly complex military systems in less time than that. NASA spent nearly 3 years recovering from a problem that many engineers had repeatedly warned about long before the disaster occurred. But it quickly became clear that fixing the O-ring would not be enough. NASA had to repair trust, the trust of the public, the trust of Congress, the trust of the people working inside the system itself. As the investigation progressed, a long list of recommendations emerged. The largest overhaul in the history of the Space Shuttle program began. More than 200 technical and operational changes were implemented before NASA allowed another shuttle to fly. The heart of that reconstruction focused on the solid rocket boosters. Engineers undertook an unprecedented redesign of the O-ring system. The joints connecting the booster segments were almost completely re-engineered. The field joint structure was modified to reduce distortion under pressure. Mechanical locking features were strengthened. Additional sealing protections were added to reduce the possibility of hot gases penetrating the seals. These changes were not simple adjustments to a minor component. They were an acknowledgement that the previous design had contained serious weaknesses. NASA also installed heating systems for critical booster components. Temperature control measures were added to ensure the seals would never again be required to operate under the extreme cold conditions seen on that January morning in 1986. Full-scale testing continued throughout the following years. Boosters were fired under a wide range of conditions. There was no longer room for assumptions, no longer room for the belief that something was safe simply because it had survived before. Yet, as the technical fixes advanced, an uncomfortable truth became increasingly difficult to ignore. Rubber was not the only cause. Steel was not the only cause. The larger problem was the way people made decisions. Investigators did not see merely a technical failure. They saw a communication failure, a management failure, a failure of NASA's safety culture. The warnings existed. The data existed. The engineers who understood the risks existed. Yet information was never transformed into action. That realization led NASA to establish new safety oversight structures with greater independence. One of the most significant developments was the expansion of safety, reliability, and quality assurance systems. The goal was to create a mechanism through which engineers could raise concerns without having those concerns overwhelmed by schedule pressure. New organizational charts appeared, new procedures were introduced, new layers of oversight were established. But one question remained unanswered. Had the culture actually changed? An organizational chart can be redrawn in a few weeks. A culture may take years. On September 29, 1988, the first real test arrived. 32 months after Challenger, America returned to the launch pad. The mission was designated STS-26. The spacecraft was Discovery. It became known as the Return to Flight mission. Unlike Challenger, the crew consisted entirely of experienced astronauts. There was no teacher, No symbolic public figure, no first-time flyer. NASA no longer wanted to take any risks with public perception. Even the mission patch carried a reminder of the past. 7 stars appeared on it in honor of Challenger's 7 lost crew members. When Discovery launched successfully, millions of Americans felt a sense of relief. Challenger had proven that technology could fail. STS-26 proved that technology could be repaired, but technology had never been the only question. In 1996, a sociologist named Diane Vaughan introduced an interpretation that would have a lasting impact on how the disaster was understood. After years of studying documents, meeting transcripts, and internal decisions, she gave the illness a simple name: normalization of deviance. The concept describes what happens when a dangerous behavior fails to produce immediate consequences. Because no disaster occurs, the organization gradually begins treating the behavior as acceptable. A small deviation becomes an exception. The exception becomes a habit. The habit becomes the new standard. In Challenger's case, O-ring erosion had been observed multiple times before the disaster. The first flight did not explode, neither did the next. Subsequent missions continued to succeed. Each successful outcome became another reason to believe the risk was acceptable. Deviation does not become normal because it is safe. It becomes normal because disaster has not arrived yet. Vaughan's concept quickly expanded far beyond NASA. It became a framework for studying industrial accidents, medical failures, financial crises, and military disasters around the world. Yet NASA's greatest test was still ahead. On February 1, 2003, the Space Shuttle Columbia broke apart during re-entry. 7 more astronauts lost their lives. This time, it was not an O-ring. It was a piece of insulating foam that separated from the external fuel tank and struck the shuttle's wing during launch. The technical details were completely different. The frightening part was something else. Foam shedding had happened many times before. NASA knew it. Engineers knew it. Previous missions had still returned safely. The familiar pattern appeared again. In 1986, it was the O-ring. In 2003, it was insulation foam. Different hardware. The same psychological mechanism. The investigations following Columbia reached a painful conclusion. Many of the organizational characteristics criticized after Challenger still existed in different forms. Years later, at an event in Washington, a woman approached Diane Vaughan. She began to cry. She said only one sentence. She could not believe it had happened again. 2 disasters, 14 lives lost, 17 years apart. The same lesson. An organization can replace engines. It can replace steel. It can replace rubber. It can rewrite procedures. It can redraw management structures. But if it does not change the way it confronts uncomfortable truths, disaster never truly disappears. It simply waits for a new form in which to return. That is also what makes Challenger different from most accidents in history. It was not the moment a component failed. It was the endpoint of hundreds of small decisions, hundreds of compromises, hundreds of moments spent convincing themselves that everything was still fine. Challenger did not explode in 73 seconds. It was built over many years before that morning ever arrived. January 28, 1986, was the day Challenger disappeared from the skies over Florida. It was the day the world watched a fireball bloom just 73 seconds after liftoff. It is also the image that would be replayed more than any other in the decades that followed. But if we look only at that moment, it becomes very easy to reach the wrong conclusion: that this was an accident, that this was an unexpected failure, that this was a disaster nobody could have foreseen. What emerged afterward pointed in the opposite direction. The O-ring did not fail for the first time on that cold morning. Signs of erosion had appeared on previous flights. High-pressure hot gases had already breached what was supposed to be safe limits. Engineers had documented these incidents years earlier. The concerns surrounding low-temperature performance were not discoveries made during the final night before launch. As early as mid-1985, Roger Boisjoly had issued clear warnings about the potential for catastrophe if the problem remained unresolved. The warning signs appeared again and again, not once, not twice. They existed long enough to become a familiar part of the system. The public saw an explosion that lasted only seconds. What investigators saw was a process that had unfolded over years. Challenger was not created during the final 73 seconds of flight. It was created through hundreds of meetings, hundreds of decisions, and hundreds of moments when risk was accepted long before launch day. The most troubling fact was not a lack of information. The most troubling fact was that many people already knew. The night of January 27th, 1986 is often remembered as the final opportunity to prevent the disaster. During a meeting that stretched on for hours, engineers presented data. They explained that low temperatures could prevent the O-rings from sealing properly. They recommended delaying the launch. They warned that there was no basis for claiming the system would operate safely under the forecast conditions. Roger Boisjoly was not alone. Alan MacDonald and other engineers reached the same conclusion. The conflict was never about missing data. The conflict was that the data did not fit the schedule. The engineers asked a question rooted in science. How do we prove that it is safe? On the other side, management gradually moved toward a different question. How do we prove that it is not dangerous? At first glance, the two questions sound similar. In reality, they are completely different. One requires evidence before moving forward. The other requires evidence before stopping. When an organization begins demanding that data support a decision that has already been made, data no longer serves its original purpose. From that moment on, engineering is no longer purely engineering. It begins to become politics. Roger Boisjoly and Richard Feynman stood at opposite ends of the system, yet arrived at the same conclusion. Boisjoly was on the inside. He saw the problem before the disaster. He tried to stop it. Feynman was on the outside. He arrived after the disaster. He tried to understand why those warnings had gone unheard. One represented the technical voice before the accident. The other represented the search for truth afterward. Both recognized that the deepest cause was not a mechanical component. It was organizational culture. During the investigation, Feynman offered an observation that became one of the most enduring conclusions of the Challenger story. For a technology to succeed, reality must take precedence over public relations. Because nature cannot be fooled. It was not merely a statement about NASA. It was a statement about every system. Nature does not negotiate. It does not vote. It does not care about budgets. It does not care about schedules. It does not care about political pressure. The laws of physics do not change because an organization wants to meet a deadline. reality remains reality. That is why the Challenger disaster reaches far beyond aerospace. For years afterward, the case appeared in engineering classrooms, management programs, courses on engineering ethics, and studies of organizational failure. People do not study Challenger simply because of an O-ring. They study Challenger because of the decision-making process behind it. One of the most widely used concepts for explaining what happened is called the normalization of deviance. The process begins simply. A deviation appears. Nothing bad happens. The deviation appears again. Still nothing happens. Then it happens again, and again, and again, gradually. What was once considered abnormal becomes accepted as normal. The danger does not disappear. Only the feeling of danger disappears. It is one of the most dangerous mechanisms inside any organization. Organizations rarely collapse because of a single decision. They collapse because small decisions are repeated long enough to become habit. That may be the final lesson Challenger left behind. At 11:39 a.m. on January 28, 1986, it was not only a space shuttle that was destroyed, not only 7 lives, not only a space mission. Something else was destroyed as well. The belief that data always triumphs over politics. The belief that expertise will always be heard. The belief that large institutions can always correct themselves before it is too late. Roger Boisjoly paid for speaking out with much of his career. Richard Feynman had to fight to ensure that key conclusions remained in the final report. Meanwhile, many of those involved in the final decision continued with their careers. There was no criminal trial, no prison sentence, no form of accountability proportional to what had happened. That is why Challenger should not be remembered merely as a technical accident. It should be remembered as a case study in how intelligent organizations can deceive themselves, how talented people can gradually accept what they once considered unacceptable, and how a system becomes most dangerous not when it fails, but when it begins to believe it cannot fail. On the day Challenger launched, the rubber O-ring was not the only thing frozen by the Florida cold. What truly froze was an organization's ability to confront reality. And when reality is no longer allowed to stop a decision, disaster ceases to be an accident. It becomes a programmed outcome.